Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, I'm going to talk about nuclear battery. So let's dive right into it. Now, what exactly we are talking about? So we have to understand we are not talking about a reactor, meaning there is no fission or fusion, meaning you are not taking two light elements, marrying them into one large one, or taking a one unstable one and breaking them apart. None of that is happening. But it's still working on E equal to mc squared. That's why you ever hear people talking about it can work for like 2000 years, 5000 years, 28,000 years. That's the reason. E equal to mc squared, the source behind. Now here's the deal. If reaction is not happening, how the heck it's still working? Well, it's radioactive decay, meaning if you are aware of periodic table, most of the things that are in periodic table, they are stable elements, meaning they're like they stay there. But between these elements, there are unstable isotope zones, meaning if you take carbon, add some extra love to it, makes a C12 to C14, it's like, bro, I'm not cool with this. That's like not stable with that. So it will try to dump itself down to chill level. Now, how does it do that? It has three modes of dumping energy. One is alpha output, meaning it just ejects a helium nuclei. Another is electron output, we call it beta rays. And then it has the ugly one, that is photon dumping, but those photons would be so high energy it will go into a spectrum of gamma rays. Very powerful, almost nigh impossible to stop. So you have these three ways of material trying to reduce its mass into energy. Basically it's too massive. It's like, bro, I'm not stable, it's dumping its mass. So basically you take element, let's say it's 1 kilogram at the beginning. Once it's completely decayed, it would have lost some mass. That mass would have went into equal to mc squared. That's how you get so much energy for so long duration without like having any consumption. Absolutely true, real. Here's a alpha, beta, gamma. That's the option. You use either three of them directly, or you can rely on the heat that is created by radiation bombardment. Meaning, if you have an element that is very radioactive and you really don't know any way of doing it, anything with it, you can just like, hey, what if we contain it into lead or cement or concrete or graphite? You contain it. It literally will absorb all that energy, which is from gamma, beta, and alpha, and then convert it into low danger, basically infrared. Basically, it will act like a step down transformer. So you will have a lot of heat coming out of it. That heat can be utilized for different cases. For example, NASA use these sort of heating blocks for deep space mission, where they are like, dude, we want this place to have at least 1 watt of heating there. They'll just put this element, because again, this will work for around decades, so they don't have to spend electrical power to heat that part up. And it's a constant warm temperature. That's good, sensors like that. So that's one of the two ways of using it: radiation bombardment or alpha, beta, gamma. Directly you figure it out. How do you use it? Now, lifespan, how long will it run? Again, that depends on element choice, meaning depending on some isotopes, you can have lifespan of 50. Depending on some isotopes, you will have lifespan of 10. Depending on some isotope, you can go to 2000 years. So element choice will define your longevity. Now, there is reasons why you do not just go like, hey, YOLO. You have to select it very wisely, because there is a consequence. Because while it is true, alpha, beta, gamma, and alpha is so weak, it can be stopped by a sheet of paper. Beta is so, again, bit dangerous, especially if it goes inside you. But like if it's outside, let's say there is this stuff that is emitting beta rays, my body can absorb it. How? The dead skin layer will absorb it and nothing much will happen. Now, here's the problem with that. All these three things have layers, specifically gamma and basically beta. They have spectrum, so to say, basically a band. Now, in that band, if the beta is very weak, it's really gonna do that. It's just gonna hit your skin cell. It's gonna heat up a little bit. Nothing much happens. But at a certain intensity, the electron could be so powerful that it dumps so much energy into receiving nucleus that nucleus is like unstable. It's like unstable. At that point in time, it dumps energy in photons that could be very high energy, as in like X-rays or gamma rays. That's dangerous. So you have to study that part also, meaning what is the oomph of the beta rays that are coming out. Will it react with the things unexpectedly, or will it have second-hand radiation output? So you have to worry all of those things in. Element choice is not just like the most powerful thing. You have to study those things also. Then efficiency, basically how much oomph you can extract out of it. E equal to mc square is powerful. Even a small stuff, plutonium or tritium and all that, just they have a lot of power. But how much can you extract out of it depends on ambient condition, generally how cool the outside environment is. And it has to be handled with care, because it's radioactive. And again, I specified beta, many times people don't take it safe, but still lethal, because again, it can create scenarios where other things are starting to dump gamma rays. And that's why, like you're talking about, things are irradiated, like how clothes and shoes became irradiated. Basically, if they receive so much bombardment that they themselves are like now unstable, they are trying to dump their energy, they themselves will become radioactive, because you have to study those things. That's why handle with care is very crucial with radioactive stuff. It's not a joke, has to be handled carefully. So first we come to the big boy, that is RTG, radioactive isotopic thermogenerator. Now these things work on radioactive decay that creates heat, meaning you take a stuff that is hot, whichever you want, you try to make it as hot as possible. You contain this puppy in some sort of armor, and that armor basically takes very high energy photons and dumps it down, basically step down transformer, steps down the voltage, increases the amps, and then you have lot of infrared photons. So these blocks could be very hot, as in like they could be generating heat of around 4 kilowatts of heat continuously for decades. Not one day, not 2 days, decades. So you have a heat source. How do you convert that into electricity? You utilize thermoelectric effect or Seebeck effect for electricity, which simply means you take two conductors that are dissimilar, meaning you take iron, copper, or two different things. And if you create this sort of winging pattern, one side hot, one side cold, you will get current flow. Like basically this sort of system. This is what is inside all sort of generators, heat source, cold side. Now, this puppy is not efficient, that's why we don't use it in coal power plants. They are very rarely 5% efficient, meaning if you have kilowatts of output, you will get hundreds of output in electrical energy. And the benefit of that, it does work, meaning moon missions use this, Voyager probes used it, and Voyager has been going on for 40 freaking years. So it does work for decades, it does provide enough power. And it does need hot stuff. That's the consequence after, meaning it does not use low grade stuff, meaning this thing will poof you out of existence if you are not careful around it. Very dangerous stuff, and it requires handling that is like done very seriously. It's not generally majority of them as gamma source emitters, so you have to be very careful around them. Now, the consequence of this, the high radiation environment harms output, meaning the generator itself will degrade. Basically, photons have pressure on things. Basically, if you have like in a photograph, it gets light bleached. How the heck that happened? Light is not radiation. It is. It literally is photon in electromagnetic spectrum. Radiation, electromagnetic radiation, it is there. It will just do very little damage. Our body can absorb it, manage it. But if you do it for long enough, it will destroy it, decay it. Just from light, just from optical spectrum, you will decay it. Now imagine having a radioactive stuff at your core. Every metal, everything will fatigue. On a molecular level, things are fatiguing. Again, it will not happen on day 1, but it will happen on day 50, day 600, day 900, day 9000. It will happen. So output of this sort of generator drops exponentially. Like you will create out a radioactive drop, is like, okay, this much, this much, this much. The real world output will be like, awesome, dead. So that also has to be taken into consideration, which source you are using and how long the mission is supposed to be. Mission supposed to be 10 years long going to Pluto, or supposed to be 40 years long. You have to select that part also. So this is the RTG. It does work awesome, but it's not something that you can see in day-to-day use. Space, awesome. Mars, awesome. Then we come to Betavoltaic. This is the part where a lot of attention is going on. Now, beta radiation has the advantage. It's not like gamma rays where it's so energetic that it just goes through things, nor it does not have the low energy of alpha, where it's like twing, bounces off things. It's high energy and speed, electron or positron. Benefit of that is charged particle, meaning it's gonna interact with thing. If you ever heard the brain damage that people have with like helium-3 reactors, it's like, why people are so excited about it? Because it's aneutronic in reaction, meaning it does not dump energy through neutron, it dumps energy through basically protons. Basically, benefit of that is the protons are charged particle, meaning you can send protons through a magnetic system and extract energy out of it. Basically, their momentum will act like a giant magnet moving through a coil, which is generator. You can get a lot of energy out of it in one step. Direct energy conversion. You don't have to boil water then run steams. Nah. Basically, proton just coming out, that will do the job. So that's why helium-3 is so desirable. Again, we have helium-3 here. We use it for quantum computer cooling. We don't use it for reactor because nobody knows how to make fusion reactor. That's why I call it stupid. But here's the same thing. If you have a charged particle, you can directly convert charged particle into electricity. We're utilizing semiconductor, P and N junction. You can utilize that. Basically, you take a stuff. Basically, let's say you take nickel 63, you put P junction, you put N junction. And you were like, wait a minute, that sounds like a solar cell. Yeah, it is a solar cell working, rather than working on photons, it is working on electrons. It works. It works, it's a long-term solution, and it's basis of almost majority of Betavoltaic systems. So you have tritium, So you have nano tritium batteries, then you have nickel 63 that gives you around 50 years of lifespan. Then you have carbon 14, the overhyped thing, the carbon nano diamond battery, and each of them have different usable lifespan, because even though on paper you may have like, hey, this is half-life of this, again depending on design, they may have designed with enough buffer that even after, let's say, half-life is over, because half-life does not mean it goes away, it's just like only 50% capacity. If it's designed in such a proper way, you can get a very long lifespan even with tritium, not just limited to 10 years. You can get batteries that are rated for 20 years. Nickel 50 years or even 100 is possible. Carbon 14 rarely used, but it can be done. Now Betavoltaic benefit is that it has charged particle output. So, and another benefit is these are not as radioactive because it's not gamma photons. You cannot stop gamma photons. These things you can stop within like tin foil. So that's another aspect of it. Now efficiency is still low. Last time we checked about efficiency, that is 5%. This is twice as that, as in 10%, but still not that high. Now there are serious about this thing has been under construction, under use, like real world deployment from as early as 1950s, 60s, 70s. Like 70s, common people started to use it. So it became a thing that has been worked on so long. They were like, why the heck no major change happened? That's the whole point. Efficiency is inherently limited. So no, people are working on design improvement, meaning because of the development in silicon industry, this was the old design. Now they are trying to do this sort of design. Now like, wait a minute, this looks familiar to semiconductors. Yeah, that's exactly how SSDs are manufactured. So if they are doing this, even if you have a limited area, like as in like say 10 square centimeter, you can have actual surface area where reactions are happening. You can have that 100 square meter or 10,000 square meter. Yes, you can amplify just by making this nano ridges. You can amplify the area. At that point in time, yeah, even a small battery will have lots of power. It can be done. Again, nobody has mass produced it, but that's current lab work. Then you have material claims, like somebody's claiming like, what if we have nickel 63 and put diamond cell or top and bottom, and we have Schottky diodes, we're gonna get a lot of power out of it, and then we stack it so we get a lot of voltage out of it. Again, it does work, it's a real thing, it does work, but none of them have like, claiming GG. Real world delivery is like barely any different than what we had for like 50 years. So that's the Betavoltaic side of things. Real world, real technology actually in use. These are used for cyber security. They work on hardware security cards, and the clocks must never go down. How do you make sure? Nano battery. Again, it's huge, but I have no idea why they call it nano. So what are the limits of this? Even though this is something that we can actually do, we know the mathematics of equal terms. It's very powerful. Now, imagine you're writing a science fiction story, have that alien gives humanity the technology of taking radioactive waste and converting 60% of that into useful electricity. It will solve entirety of human problem like this. Entirety of human problem. The gun, no problem. Like water crisis, dude, drain freaking sea. We can do that if we can extract 60%. I'm not even talking 100, not even 90, 60, done. Don't think about it. Like energy, we'll never worry about energy. That's how much power is there in there. But we are only able to extract 10%, is useless. So that's the reality of it. Now, why is that happening? Because there are some laws of physics. Now, this goes into very deep advanced nuclear physics, which is far beyond my understanding. But think of it this way, it's very similar to what happens in solar cells. If you have single junction solar cells, like let's say silicon junction solar cells, no matter what you do, you cannot exceed 35%. Like there is a law, you cannot break it. And when military have to put spy satellites, they consume a lot of power. They have the issues like if you put giant solar panel, people can see it, people can track it, and they can block their view. So what they do, they put very small panels. How do you get so much power out of this? Multi-junction solar cells. So those solar cells can have 2 junctions or even 3 junctions. At that point in time, some claims are like they are 53% efficient. That's bonkers. That's bonkers. That's ludicrously bonkers. So same way there was a physical limit, like no matter what you do, you cannot cross 33%. Similar things happens in the Betavoltaics, and even on RTG. Like there are certain laws. That's why we are not like able to push like 20%, 30%, 40%, 50%. We are not able to do that. There are laws that we cannot just break. And then we come to real aspect of it, is that nuclear safety is not cheap. Like this is a very ancient device. Armco Medical Products Corporation pacemaker NU5F. These are old devices. We used to exist. Now these have battery life of around 80 years, 88 years in some cases. And you can see it has plutonium-238. Now, problem with these things was like they're supposed to be sold to people. Awesome. People supposed to use it. Awesome. When they died, this supposed to be returned to the company that sold this part. Like at least call the basically Armco company that we have your pacemaker. Can you collect it? And they will send agents to collect it, because again, plutonium-238 is not something that you can cremate someone with. And unfortunately, many people did that. Unfortunately, many people took that and buried that, and that created consequences for corporations where they're like, dude, government was like, dude, you sold, let's say 1 kilogram of show the return of it. So the decayed product of it, they can't. So many companies literally went under, and nobody wanted to deal with the hassle. Think of this, like these things used to exist, used to give you 88 years of lifespan. Right now moderns are like 10 years. So think of this, especially if a pacemaker is needed by a child, that's a very brutal, like every 10 years brutal. So nuclear safety is not cheap. Like even if you took at this nano tritium battery that contains helium-3 tritium max activation, these things you can make at your home. I provided the video down below. It will work, and it will work better than this. Again, it will be bigger, but it will work. But problem would be you do not have this required license to make it nuclear safe. The moment you try to get that, the cost goes YOLO. So even if the physical cost of making this puppy could be as little as, let's say, $300, you have to charge $3,000 for that. Same goes with this. This is some Russian design of N nickel 63. That's 2 volt cell. Now this is the size of it, and it powers that tiny watch. So basically, if you want to run a smartphone, imagine a briefcase size battery, big briefcase, maybe a small phone with that. Now, nuclear safety is not cheap. Although, if it was valuable enough, people will figure out a way. People will figure out a, like we use many dangerous things in our day-to-day life. How? Well, it's useful. We figure it out. But here's the power output of this sort of technology. It's uselessly low. Like it's so low that most people have no inherent concept of how low it is. And this personally boils my blood every time I see engineer Indian YouTubers where they're talking about like this battery will run mobiles and cars and all that. I'm like, do you not understand nanowatts? Like microwatts. Like this microwatt, you need to have around basically 1 billion of it. 1 million microwatt to have 1 watt. Like there are 6 zeros here. 6 zeros. Like this sort of cell, they gives you around 20 microwatt. So if you buy this sort of system, they will give you a chart of it. Chart is like year 0, meaning after the manufacturing, it will be 100 microwatt of power. Then it will, like year 10, it will be 56 microwatt of power. Year 20, it will be 32 microwatts of power. So if you're designing it a circuit that has to be validated for 20 years, you will design your equipment to work as low as 25 microwatts. That's very low. That's like, you still have too many zeros left. That's why you cannot just again, think of this like this is a giant thing, and that all that's powering is that tiny thing. Now, is this useful? Again, for certain industry, they are like, shut up and take my money. But for day-to-day use, hell no, 100% useless. Because like most people don't know this conversion. That's the thing that really boils my eyes. Like if you try to run a car with that good freaking luck. So that's why even though these things have been existed for long ago, we never oh, why doesn't your mobile phone has this? That's the reason for it. It just does not have enough power. So hype is the thing that basically pisses me off a lot, simply because a hype is doing something very cruel. It's like they're taking half truth, and like because there is truth, it deviates your filter and then it just feeds you lie. So the truth part is a battery that lasts forever. That is true. Now, what does forever means? Forever simply means something that is extending beyond human lifespan. For example, if a human is there, you will expect anything that crosses 100 years is like, dude, this is a lifetime product. 100 years, lifetime product. Or even 88 years, practically speaking. So that part is absolutely true. Real world, here it exists. Truth. It can power your car. That's false. That's just no. That's just like no. Because battery size would be size of a locomotive, and it will be powering up the smallest car that you can think of, street legal car. And good luck, it cannot have that kind of tonnage pullage capacity. It has to literally be plugged into that kind of battery. That's why you do not see this sort of thing used in drones and military system. It's like, yeah, can it work? Absolutely. But even military could not figure out how to use these things. It's like, okay, at least how about a radio battery? They're like, shut up and take my money. It's like, imagine a radio battery that works for a decade. It's like, shut up and take my money, but it just does not work. Like this nano diamond battery, all the garbage that happened with this, it's like, this is the company that is giving CGI, and it's like fake CGI you are selling to people, and at least they did their due diligence in first one. It's like 100 microwatt. The moment people started reading that, they updated the image, they removed that 100 microwatt output. Because again, you have to understand this as well. Most people don't sit down and think about what is the relationship into kilowatt to kilogram. It's not your job. It's the job of, let's say, Samsung engineer. Like for example, if a Samsung engineer is like, I'm making a mobile phone, let's say F62. Is supposed to have 7,000 milliamp hour battery. So they have to figure out, it's like, okay, the maximum weight that people can comfortably handle is 250 grams. How can I fit everything else? They have to figure that thing out. You don't think about it. It's not your job. But if somebody shows you lithium ion works for 8 hours and nano diamond battery will work for 28,000 hours, I'm pretty sure it will not last because of the radiation. It's like that radiation will inherently decay that puppy up. So let's say anything crossing 100 is pointless at that point in time. It's like 100 years. You will believe that, because it's not your job. It's like, hey, wait a minute, this has microwatt output, that has few watts of output, like 5, 10, even 11 watt battery exists in your mobile phone, and it goes through that in a day. This does not have enough power. Like, and then they'll, like, half truth. It's like, we're gonna charge super capacitor with this and they're gonna give you 1.5 volts. I'm like, yes, you can do that. It's just that it will not have amps. It will not even have microamps. It will have nanoamps from it. That's the whole thing. It's like, even if you charge that puppy up for 23 hours, in that 1 hour, good luck trying to find anything that can use that. So that's the whole thing, that how many zeros are there in microwatt. It's not common. Like, think of this way, like normal meters, they don't have that port. Like, you have to buy some high quality meters that has that microwatt port. So that's the whole thing. It's really, really frustrating, because it's a good technology. It's a really good technology. If proper Betavoltaics become a common thing that is using nickel rather than plutonium, it will be awesome, and it will help a lot of people in need. And there are many things that will be immensely benefited by that, but not in day-to-day use. And because of this sort of overhype, overpromise, under-delivering, it will burn people out, and burning people out removes money from stock market. People remove money from stock market, this sort of research gets canned, because again, companies like not seeing that investment, they're like, bro, I'm pulling out. So you see that, like, hype is dangerous. Like, how many see, I'm like, this is gonna imagine an electric car that never has to charge. I'm like, if we could have done that, we would have done that in 1970. There is a reason we don't do that. Physics does not allow it. Like, that's how I will write my science fiction. It's like some alien figured out a technology to give 95%. That would be horrifying if true. So that's the hype part of it. So this was my presentation on nuclear battery. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.